Bounded versus unbounded feasible regions. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to recap what we've covered so far. In our previous lessons, we practiced how to take a set of mathematical constraints and plot them on a graph to identify what we call the feasible region, that specific area where all our conditions are satisfied simultaneously. Now, as we move forward, you'll notice that not all feasible regions look the same. Depending on the type of constraints you are working with, this region can take two different forms. It might be a closed shape, which we call bounded, or it might be open-ended, which we refer to as unbounded. It is incredibly important that you learn to distinguish between these two. Why? Because this distinction is critical for solving optimization problems. It actually determines whether we are guaranteed to find an optimal solution, meaning a definitive maximum or minimum value, or if we might run into a situation where a solution simply doesn't exist. So, let's take a closer look at each of these types in the next few slides. 1. Bounded feasible region. Now that we've established what a feasible region is from our previous discussion, let's dive into our first specific type, the bounded feasible region. Mathematically speaking, we say a feasible region is bounded if you could theoretically draw a circle around it with a finite radius, and the entire region would fit comfortably inside that circle. To put this in simpler terms, think of the region as being trapped or fenced in on all sides by your constraint lines. There is no way for the region to escape or leak out into infinity. There are three key characteristics you should remember for your exams. First, the region does not extend to infinity in any direction. Second, it forms what we call a closed polygon, a shape with distinct straight sides. And third, and perhaps most importantly, there is a guarantee of optimality. This means that if your region is bounded, your objective function, which we represent as z equals a times x plus b times y, is guaranteed to have both a maximum value and a minimum value. And here is a great shortcut for your calculations. Both of these optimal values will always occur at the corner points or the vertices of the region. Make this more concrete, let's look at a real-world analogy. Imagine you are running a small business and you have a fixed amount of budget and a fixed amount of storage space to stock two different products. Because your money and your space are limited, there is a natural ceiling to how many products you can possibly acquire. You can't buy infinite stock because you'll eventually run out of cash or room. Therefore, your possible production options are confined to a specific, limited area on your graph. In the next slide, we will look at the opposite scenario. What happens when those boundaries are removed and the region becomes unbounded? 2. Unbounded feasible region. Think of an unbounded region as the complete opposite of what we just discussed. We say a region is unbounded if it is impossible to enclose it within a circle of any finite radius. In simpler terms, this happens when the shaded area on your graph extends indefinitely in at least one direction. It just keeps going and going toward infinity. Let's break down the key characteristics so you know what to look for during an exam. First, unlike the closed polygon we saw in the bounded example, an unbounded region is open on one or more sides. You'll notice this typically happens when your constraints use the phrase "at least." For example, if you see an inequality like x plus y is greater than or equal to 10, you are shading the area away from the origin, which leaves the region open. This is a contrast to the, at most, constraints, like x plus y is less than or equal to 10, which we saw in the previous slide. Now, I want you to pay close attention to this optimality warning, as this is where many students lose marks. In an unbounded region, a maximum or minimum value may or may not exist. This is a big difference from the bounded region, where a maximum and minimum are guaranteed. If your region extends infinitely in the positive direction, a maximum value might not exist at all, because your objective function, z, could simply keep increasing forever. However, there is one silver lining. If an optimal value does exist, it will still occur at one of the corner points. To make this more concrete, let's use a real-world analogy. Imagine you are working with a nutritionist. They might require that a diet contains at least a certain amount of vitamin A and vitamin C. This creates a floor or a minimum requirement that you must meet. But is there a theoretical maximum to how many vitamins you can consume? Not really. You could technically consume an infinite amount of vitamins. Therefore, your feasible options extend infinitely upward on the graph. Now that we have understood how a bounded region is trapped or fenced in, let's look at the opposite scenario on slide 3, the unbounded feasible region. In the next slide, we are going to look at some specific mathematical examples to see exactly how to identify these two types of regions in practice. 3 illustrative examples. Now that we have covered the theoretical definitions of bounded and unbounded regions, let's put these concepts into practice with 2 illustrative examples. This will help you see exactly how the direction of the inequality changes the shape of our feasible region. First, let's look at example A, which represents a bounded region caused by resource limitations. Imagine a small business that produces 2 different products, which we will call X and Y because resources are limited. The business faces a total production limit, expressed by the inequality. X plus Y is less than or equal to 10. We also have our standard non-negativity constraints, meaning X is greater than or equal to 0, and Y is greater and equal to 0. Let's break down the analysis step by step. To graph this, we first look at the boundary line, which is X plus Y equals 10. This line connects the point 0, 10 on the y-axis to the point 10, 0 on the x-axis. Because our inequality is less than or equal to, we shade the region towards the margin. When we combine this with our non-negativity constraints, we find that the feasible region forms a closed triangle with 3 corner points, or vertices, 0, 0, 10, 0, and 0, 10. As we discussed in the previous slide, because this triangle is a closed polygon that can be completely enclosed within a circle, we classify this as a bounded region. The most important takeaway here is that for any objective function, z, there is a guarantee that both a maximum and a minimum value exist, and you will find them at one of these 3 vertices. Next, let's contrast this with example B, which shows an unbounded region. In this scenario, a factory has a contract to meet a minimum production requirement. This means the constraint is X plus Y is greater than or equal to 10, along with our usual X and Y are greater than or equal to 0. Let's analyze this step by step as well. The boundary line is the same as before, X plus Y equals 10, connecting the points 0, 10 and 10, 0. However, because the inequality is greater than or equal to, we shade the region away from the origin, moving into the upper right area of the graph. This region starts at our boundary line and extends infinitely into the first quadrant. Since this area stretches out forever and cannot be enclosed in a circle, it is unbounded. Now, pay close attention to the implications for optimization, as this leads into the warnings we will discuss in the next slide. In this unbounded case, if our goal is to minimize cost, a minimum value likely exists at one of the corner points. But if we are trying to maximize profit, the value of z could potentially increase toward infinity, meaning a maximum value might not exist at all. Keep these differences in mind as we move on to look at some common mistakes students make when solving these problems. 4 common mistakes to avoid. First, be very careful about assuming that a maximum value always exists. It is a very common mistake to find a value at a corner point in an unbounded region and immediately declare it the maximum. Remember what we discussed in slide 3. Because an unbounded region extends infinitely, the objective function could potentially increase forever. So, if you are working with an unbounded region, you cannot just stop at the corner point. You must perform an additional check, such as using the open half-plane method, to verify if that value is truly the maximum or if the function just keeps growing. Second, please do not confuse an unbounded region with having no solution. These are 2 very different things. An unbounded region does not mean the problem is unsolvable. It simply means the area we are looking at is infinite in size. As we saw in our factory example, you can still find a very clear minimum value even if the region is open-ended. The solution exists. It's just that the ceiling or floor might be missing. Finally, never forget the non-negativity constraints. It is easy to get caught up in the complex inequalities and forget that x is greater than or equal to 0, and y is greater than or equal to 0. If you ignore these, your mathematical region might extend into negative quadrants, which leads to results that are physically impossible in real-world scenarios, like producing a negative amount of a product. Now, before we wrap up with our summary, I want to pause and discuss some common pitfalls. As we've seen in the previous examples, distinguishing between bounded and unbounded regions is vital, but even when you identify the region correctly, there are 3 specific mistakes that often trip students up during exams. Keep these corrections in mind as we move to our final slide, where I will provide a quick comparison table to help you consolidate everything we've learned today. Key takeaways. Now that we have walked through the definitions, the real-world analogies, and the specific examples of both types of regions, let's bring everything together with this summary table. This is a great tool to use as a quick reference for your revision. Let's look at the first row, visual shape. As we discussed earlier, a bounded region is a closed polygon. Think of it as a fenced-in area. An unbounded region, however, is open-ended, meaning it stretches out indefinitely. Moving to the second row, we look at enclosure. This is the mathematical definition we used. A bounded region can be completely enclosed within a circle of a finite radius, whereas an unbounded region is so large that it cannot be enclosed by any circle, no matter how big you make it. In the third row, we address the most critical part for solving optimization problems, the existence of a maximum or minimum. In a bounded region, you are guaranteed that both a maximum and a minimum value exist. But, as we saw in our unbounded example with the nutrition requirements, in an unbounded region, a maximum or a minimum may or may not exist. The fourth row, location of the optimum, is a very important tip for your exams. For a bounded region, the optimal value is always found at one of the corner points or vertices. For an unbounded region, the rule is slightly different. If an optimal value does exist, it will still occur at a corner point, but you must be careful to check if the function could actually increase or decrease infinitely. Finally, the fifth row shows the typical constraints. You'll often notice that bounded regions are created by less than or equal to constraints, which act as ceilings. Unbounded regions are often created by greater than or equal to constraints, which act as floors. Keep this table in mind, as it summarizes the core logic you'll need to master linear programming.